In these videos, I would like to discuss about the multiplication in frequency domains. I believe that I already give you some exposed to image enhancement in frequency domains, where actually that is not included in this course, okay, which is not included in your test or final exams, okay. But when we talk about the frequency domain, why we need to know a little bit about the concept of frequency domain, because that is where you need to know that things, because that is the one that we discuss in chapter 5, where when you want to deal with condition number 2 and condition number 3, okay, when the degraded image G is degraded, okay, the image G is degraded with degradation function as well as noise, okay. So that is where actually applying the frequency domain is important. And then the things that I already discussed earlier is that when you apply some filter, okay, in time domain or in spatial domain, actually you will perform the convolution operation, but when you deal with the frequency domain, that operation become multiplication, okay. And the one that might be I think I want to extend further to discuss about the multiplication, because I hope that by having this kind of discussion, then it will make you more understand about the multiplication process in frequency domain, okay. Actually, when we talk about the multiplication, is a similar typical multiplication operation, okay, meaning that, okay, for example, like what we have discussed in chapter 4, okay. For example, this is your image, okay. For example, this is your image, okay, your image F in spatial domain. Then if you convert into Fourier, if you are convert into frequency domain, okay, same using a Fourier transform over here, okay. If you are using the Fourier transform to convert into frequency domain, then of course if this is the image, and then if you convert into Fourier transform, or if you convert into frequency domain, then you will see the same size image, but of course you cannot see the picture anymore, okay. For example, this one I just draw some, there's a people in this image, but if you convert into frequency domain, it will provide some image matrix where the size is similar with the original image in spatial domain. But if you display, it's provide some kind of pattern, but it's not very meaningful, or cannot be interpreted what image is that, because in frequency domain now it's become the information, there's a numbers there, there's an image matrix there, but if you display that image matrix in picture, then you cannot interpret something, okay. That's why I just draw, let's say if you have this kind of image, you convert into Fourier transform, then this is how it should like, meaning that it's a meaningless image, you cannot interpret some things there, okay. So what happened is actually the one that I don't discuss is that, let's discuss a little bit on the basic of Fourier transform. So at least you know what happened, so you can relate this knowledge with the concept that you have learned in chapter 5 later. But of course, this one again is just for your additional knowledge, so it will make you better understand what happened is in chapter 5, okay. So let's say this is your image, okay. For example, this is your image matrix 2. If you talk about some small image, is a 2x2 matrix image in spatial domain. So of course you have the numbers here, okay. I just put here as A1, A2, A3 and A4. So if you apply the Fourier transform, okay, it's similar to what happened in one-dimensional signal. So if you apply any time domain matrix, one-dimensional signal, one-dimensional matrix, or one-dimensional signal, if you apply the Fourier transform, then what happens is actually it will give you, instead of one-dimensional matrix, it will also provide here if you talk about the two-dimensional signal like image, if you apply the Fourier transform, then it will provide the similar size of 2 times 2 image matrix like the original matrix that in spatial domain. However, the numbers here is already in the the output here is the output after you apply the Fourier transform. In general, when you apply the Fourier transform, the output here instead of real number it become a complex number. Okay, if you remember about the complex number, okay, real number is you only have the real number, okay, which is either 1, 2, 2.5. But if you talk about the complex number, it could be like 1 plus j3, that is complex number, and let's say 5.5 plus j 4.5, so this is complex number. So what happened when you apply, okay, you can try this, you can try to apply the Fourier transform, two-dimensional Fourier transform in MATLAB, and you apply to the two-dimensional image like this, then you will realize that here you will get the result in form of complex number, okay, such as this one should be x1 plus jy1, this one is x2 plus jy2, and so on. Okay, so of course this is in Cartesian coordinate. Okay, you can also change into a polar coordinate. Okay, in complex number it's a similar. Okay, it should be r1 theta 1, then r2 theta 2, and so on. Okay, so that's how if you apply the Fourier transform. So that's why the one that we don't emphasize, but it's better to get some additional knowledge, even it's not a cover later, but it's better for you to get the concept, then you know how to relate this one with chapter 5. Okay, this is why when you apply the Fourier transform of this image, okay, this slide is in chapter 4. Okay, so the slide in chapter 4. Okay, that's why when you apply the Fourier transform of this one, then you get two matrix here, because this one is already separate between the real and imaginary. Okay, if you remember this one, yep, this one. Okay, this one I merged together, so that's why it become a complex image matrix. But this one can also, you can change into, you have here r1, r2, and so on, and this one you only put as a theta 1, theta 2, and so on. So you separate the real component and imaginary component into two matrix. So that's why if you see in this slide, okay, it's already separate that. Okay, in other words, actually this matrix and this matrix is merged together in form of complex number. Okay, when you apply the Fourier transform, so that is what happened. So when you display the image, of course the image, like I said, in real application you cannot see, you don't see, it's a meaningless image. Okay, so that's why let's go to some practical example. I don't want to discuss this one. Let's go to the practical example, like this one. Okay, this one, okay, this is your input image. If you apply the Fourier transform, if you apply this image with Fourier transform in order to convert it from spatial domain into frequency domain, then it will become like this. Okay, so it's a very meaningless image. Okay, you don't know what is it, what image is this. Okay, unless if you inverse back to the spatial domain, then you know actually it's a image of fruit there. Okay, so that is what happened. Okay, that is the fact what happened actually when you apply some image in spatial domain and you apply Fourier transform, you see something which is meaningless. But again, when we try to multiply this one with some filter, again when we do some process, okay, when we do some process, okay, you give your input image here, I write it in frequency domain, and then you have some filter here, and then you want to get some some output here. Okay, so this one now is become multiplication, okay, as in theory. okay, it will become the multiplication. Okay, multiply with your h. So let's assume that your h is actually, your h here is a low pass filter, okay, an ideal low pass filter. So we have discussed before how the ideal low pass filter is look like. It's something like this, okay. It's in form of cylinder, okay, where this is actually the radius here actually is a cut-off frequency. Okay, we don't call it FC as in one dimension signal. Normally we just call it as R. I think it's R, right? In the slide we talk about that one. Sorry, D naught. Okay, it's not R, D naught. Actually it's D naught, but it's a radius. Okay, D naught. Okay, we use as a D naught. This one become D naught, but it's look like a cylinder. Okay, the rest is 0, only the one that inside the circle here, this surface is 1. Okay, so this is in 2D. So if you draw it in image matrix, then your h it's okay, your h should look like this. Okay, the circles, and then the rest here is 0 0 0 0. If you zoom, you can see that all matrix here is 0 0 0 0. Only inside here is 1 1 1 1 1 1 1 1. Okay, so that is, just assume, okay, if this is the image matrix of your G, of course this filter, the size of matrix is similar to this input image. So if you multiply, sorry, this is not G, this is your H, and then if you multiply with your original image, which is this one. Okay, I just drag this image into this position. I just draw back the, okay, you don't see anything here, okay, something like that. Then you do a multiplication between this F and this F and this H. So what happened, so that's why at the end the product of these two, okay, finally you will get something like this. So this is your G UV, okay, because the one that inside the circle here, will be retained, the rest will become 0. Okay, it's a typical multiplication operation, so that you don't have to worry about it. So you just draw, your G might look like, if this is the circle, I just draw it. I just impose this H into my F. So I draw the D naught there, the D naught circles there. So anything here outside here becomes 0, and the one that inside here will retain. So in other words, if I draw the output will, look like something like this. Okay, then you will have, the blue one, okay, the one that something like this, and then you have a something like this inside. So the rest here will become 0. The rest is 0. The only information remain is the one that inside the circle. Okay, what is the information inside the circle? Of course, it's come from your F here. Okay, so that's why after that, if you want to know what happened, then you need to inverse back into your G, X, Y by applying the inverse Fourier transform. So then you can have some meaningful image. Then you can see what happened after you apply. So that's how. But the one that I want to highlight here is when we talk about the multiplication, doesn't matter is it a multiplication or division, then this is happen. This is what happened. It's a typical multiplication. It's a multiplication between matrix. Okay, meaning that that's why if the filter is an ideal like this, then anything 0, then this matrix over here multiply with 0. That's why it becomes 0 here. But anything's inside here, because it's this one multiply with 1, so that's why at the end you are retain the same information as what we have in our F here. So it's a typical multiplication operation. Okay, it's not don't think about the complex thing. Okay, it's a typical multiplication, but now just imagine the multiplication is between two matrix. Okay, so that's why now you are just imagine that when I talk about multiplication, is a multiplication between two matrix, and there's no any complex things there. Okay, still the operation is the same, typical multiplication, just the difference is that now we have the operation of multiplication between two matrix, where that matrix is the same size. Okay,